Okay, this is class example problem unit E1 and page 9. This is the only example of unit E1. Let's take a look at the problem. This example problem tells you exactly why we conduct the experiments, and then based on the data sets we obtained, what kind of conclusion do we need to draw, and then how can we interpret those results. Okay, so let's take a look at the pressure drop. Here we go. The pressure drop delta P over a certain length of horizontal pipe is assumed to be a function of multiple things. Function of velocity B of the fluid in the pipe diameter, and the fluid density and viscosity. So delta P depends on velocity, diameter, density, viscosity. Depends on 4 different variables. Okay. A. Show that this flow can be described in dimensionless form as a pressure coefficient Cp as defined as this, that depends on the Reynolds number. So we are going to apply Buckingham Pi theorem to confirm that original definition of delta P as a function of 4 different variables can be represented by 2 dimensionless properties. Okay? And part B, the following data were obtained in an experiment involving a fluid with this fixed density and viscosity and fixed diameter. So if you fix density, viscosity, diameter, you measure delta P based on the variable of velocity of the pipe. Plot a dimensionless graph and use a power law equation to determine the functional relationship between the pressure coefficient and the Reynolds number. C. What are the limitations on the applicability of your equation obtained in part B? Okay. So step by step. So what kind of problem you're trying to solve? So this is a pipe flow. Okay. Most important design factor of the pipe flow is how much loss do you have for the pipe. Loss of the pipe is going to reduce the pressure. So let's see. This is a cross-section 1, pressure is P1. This is a cross-section 2, pressure is P2. So let's say this is the horizontal length of the pipe, the length L. So over a given length of the L of horizontal pipe, how much pressure drop do you have? Delta P is P1 minus P2. This is very important design factor of the pipe. Everybody wants to minimize this because this is essentially the loss of the pipe. If you have a large pressure drop on the pipe, you have to add huge pump to deliver liquid within the pipe. Okay? So our purpose here is, let's analyze what is the contributing factor of this pressure drop. We do know delta P depends on multiple things. Delta P is a function of, okay, let's be careful. Delta P can be expressed as a multiple functions of multiple dependent functions. So delta P changes if you change, for example, velocity of the pipe. So pressure drop depends on what is the velocity inside of the pipe. Yes. So delta P also depends on diameter of the pipe. Yeah. Okay. And then type of the fluid inside, of course. Density of the fluid inside of the pipe. So delta P also depends on that. And also viscosity of the fluid. So delta P depends on multiple variables: velocity, diameter, density, viscosity. So that much we know. Okay? So this is the expression saying delta P is a function of velocity, density, velocity, diameter, density, and viscosity of this pipe flow. Okay. So let's apply part A. Let's apply Buckingham pi theorem. Applying Buckingham pi theorem. Buckingham pi theorem, K minus R. Okay? So first of all, K is the number of independent dimensioned variable which is involved in the problem. So K, let's count. Delta P is one of the independent variable. Velocity, diameter, density, and viscosity. Those are 5 independent dimensioned variables is used. Those are the 5 variables used to describe this original problem. This R is, if you take a look at each one of those, how many basic dimensions do you need to describe each one of those? Okay. So velocity is length over time. So length and time, those are the basic dimensions used. This is diameter, which is length. Density is mass over length cube. So as it seems like mass, length, time, all three basic dimensions are used. So if that's true, K minus R is 5 minus 3. It's going to be 2. So Buckingham pi theorem says this original problem can equivalently be expressed by using 2 independent dimensionless variables called pi terms. So this is the original problem. Delta P is a function of 4 different things. However, through Buckingham pi, you can represent the same thing using this. Okay? If you combine delta P, this is a pressure change, so the unit of this is pressure. Okay? Divided by density times B squared. Density is mass over volume. This is length over time, taken squared. If you stop and think about it, if you combine delta P density velocity square, you are going to cancel out all the units. So this is dimensionless. There's no unit associated with. Now, oftentimes we are going to multiply by 1/2 in the bottom. Why are we doing that? 1/2 is, by the way, constant, so it doesn't change the unit. 1/2 rho v squared is dynamic pressure in Bernoulli's equation definition, so it's convenient. So this is the dynamic pressure, this is the pressure change over the length L. This is a function of another thing. Let's combine density, velocity, diameter divided by viscosity. As you may know, this is something called Reynolds number. This one doesn't have units. Okay. Once again, I'm going to use this. This is the meaning of function of. Okay. So this is called pressure coefficient, Cp. This is called Reynolds number. Okay? So this is the expression, equivalent expression using two-dimension. This property is called pi terms. This original program statement, let me just write it down here. So this is the original program statement. Delta P depends on, well, I would say delta P is function of velocity, diameter, density, viscosity. Alternatively, you can say delta P is a function of velocity, diameter, density, viscosity. Alternatively, you can express the same program, Cp is a function of Reynolds number. Or you can say Cp is a function of Reynolds number. Okay? Cp is a, again, different function of Reynolds number. I'm not using this f here. I'm using phi instead of f. Why is that? Because Cp is a function of Reynolds number, but the functional relationship between delta P and those and Cp and Reynolds number will be a different function. That's why I'm trying to avoid using f here. This P represents Cp depends on Reynolds number. In other words, Cp is a function of Reynolds number, but it's going to be not the same functional relationship with that. Okay? So let's be careful about that. This P is not the mathematical multiplication. This is just an expression saying Cp depends on Reynolds number. Delta P depends on those. Okay? Alright. So I guess let's move on to part B. Part B. So part B is the reason why we conduct experiments. We want to find out, okay, exactly what is this relationship then. You are basically telling me that Cp, pressure coefficient, depends on Reynolds number. So that means Cp is a function of Reynolds number, some kind of function of Reynolds number. So what exactly is such a function? Can you give me a functional relationship? Functional relationship really is, usually do we have an equation actually relates Reynolds number to pressure coefficient? Yes, we do. And then oftentimes, how can we determine such a thing? We conduct the experiment. Okay? That is the reason why we oftentimes do experiments. Experiments usually is smaller scale, and then it is acceptable because Cp and Reynolds number both, those are dimensionless. So it does not depend on the size. Okay? So that's something called similitude concept. But let's take a look at what kind of experiment we conducted. Let's go back to this original program statement. Okay. So now we decided to conduct experiments. The purpose is to find out mathematical functional relationship between Reynolds number and pressure coefficient. Okay. So this is what we did. We did experiment. Then usually experimental setup is usually constrained. So this is our constraint. We use the density of fluid, 2 slugs per cubic foot. So in other words, we conducted this experiment using maybe water. Water comes with certain density and viscosity. Diameter of this experiment is 0.1 feet diameter. You can conduct a different diameter, but in this particular case, we did the experiment using diameter 0.1 feet. Okay? Then what we did, let's come up here. So we tested using diameter 0.1 feet pipe. Density and viscosity of the flowing fluid is water, so water property comes in. So what I did was I changed the velocity. Velocity, if the velocity is 3 feet per second, what is the pressure drop? Pressure drop can be measured, right? You put the pressure gauge here, pressure gauge there, you determine the pressure difference over the length L. So you can measure delta P with variable velocity. Velocity is 3 feet per second, 11 feet per second, 17 and 20 feet per second. You determine the delta P. You measured it. Okay? Then you came up with experimental results. Okay? So this is velocity, feet per second. This is delta P you measured, which is L per square foot. So what I did was, starting with 3 feet per second velocity, next is 11 feet per second, 17, 20 feet per second velocity. So based on each different velocity, we defined what we measured, the P pressure drop here. So this is 192 PSF, 704 PSF, 1088, 1280 pound per square foot. So this is just experimental results. Now, most importantly, why did we conduct this experiment? What kind of information do we want? Our purpose is to determine this functional relationship between pressure coefficient and Reynolds number. So, first of all, let's find out Cp. Cp, as a definition, this is delta P divided by 1/2 rho B squared. Right? So now delta P is delta P we measure right here, 0.5. Density was fixed. We used water, so 2 slugs per cubic foot density, constant. And velocity B squared. Okay? Velocity B is also variable. It looks like 0.5 times 2 cancels out. So this is going to be delta P divided by B squared. So this is Cp. So you can actually add some more of the data to this table. So this is a raw result. These are the calculated results you're going to add. Okay? So based on this equation, for a given delta P and B, you can determine Cp. Okay? Well, what about Reynolds number? Reynolds number, by definition, this is rho Bd over mu. Okay? Density is once again 2 slugs per cubic foot. Velocity is b. Diameter we chose 0.1 feet. Viscosity is 2 times 10 to minus 3 pounds second per feet squared. So we can simplify 0.1 to 2 times 10 to the minus 3. This is going to be 100 times b. Okay? So Reynolds number is essentially this multiplied by 100. So now what I'm going to do, I'm going to, let's use the Microsoft Excel spreadsheet. Okay? Then I'm going to show you demo. So let's go back to the screen. So I'm going to run, first of all, spreadsheet. Typical spreadsheet you use will be Excel. So here we go. So this is a Microsoft Excel spreadsheet. So you're going to use this probably in your experiment. So let me just zoom in a little bit more. So let me just give you, this is the raw data, velocity. So velocity is 3 feet per second, 11, 17, 20 feet per second. So those are the velocities. Test conditions. So this one is delta P. Delta P is pound per square foot. Let me just change the font here to symbol. Turn it to delta. Okay? By the way, this one. There we go. So this is delta P. Delta P is the pressure difference you measured. This is given 192 psf, 704 psf, 1088 psf, 1280 psf. Okay? So those are the measured value, condition, test condition, and result which you measured. Okay. Now out of those, you are going to calculate the Reynolds number and pressure coefficient. Reynolds number, pressure coefficient, they don't have units. Okay. We do know Reynolds number is equal to 100 times velocity. So if the velocity is 3 feet per second, Reynolds number is 300. So I'm going to just copy, paste cells. Here we go. I just computed Reynolds number based on the given velocity. Okay? Good. Let's just zoom in a little more. Pressure coefficient Cp is given by delta P divided by velocity square. Velocity square. Okay, so I got that. This is the pressure coefficient. I'm going to copy paste cells. There we go. So this is calculated Cp. All right. So what are we going to do? Our purpose here is to find out the relationship between Reynolds number and Cp, because we know pressure coefficient depends on Reynolds number. So what kind of relationship do we have? Well, that's why we want to plot our results. That's the reason why we plot. Plot tells you the relationship between those two variables. So let's plot. So I'm going to plot Reynolds number and CP. Insert chart. It's going to be XY scatter plot, just like so. Okay, here we go. So this is the plot based on the data set. Okay? So it looks like this is the CP. Well, we'll use that label. I don't need the title, so I'm going to remove the title. Okay, so let's insert axis titles. So let's say primary horizontal axis is, of course this one is Reynolds number, right? So this is x axis is Reynolds number, and then y axis title primary vertical. Of course, this one is pressure coefficient. Okay. So you are plotting Reynolds number versus pressure coefficient plot. You have 1, 2, 3, 4 data points. Okay. So this is the plot. What does the plot tell you? This plot tells you the relationship between Reynolds number and pressure coefficient. Okay. Well, I'm not satisfied. I really want some kind of mathematical formula that actually relates Reynolds number and pressure coefficient. Can we do such a thing out of the data? Yes, we can. That's something called curve fit. Let's do curve fit. So how do you curve fit? You're going to choose the data you want to curve fit. So those are the 4 data points. You're going to insert trend line. Look at that. Add trend line, which is curve fit. So you are going to add the trend line. So now it is going to show you multiple options. How do you curve fit these 4 points data? Do you want to curve fit with linear equation, exponential equation, log, polynomial, power? What is it? Well, looks like this is a linear curve fit. Well, it's pretty bad, huh? Because it doesn't look like linear. Okay, so let's just choose different options here. How about exponential curve fit? Oh, it's much better than linear. However, are you happy about that? There's quite a bit of errors here, especially for low Reynolds number range. How about log? Oh, this is a little bit better. You know, it tries to fit right here. Yet, you're going to introduce some error in higher Reynolds number range. Not sure. How about polynomial? It's kind of reverse trend. You know, this one decreases, but the polynomial curve fit seems to be there, goes up. I'm not sure about this. How about power? Whoa. It looks like this is it. Okay? So I'm going to choose this curve fit. I'm using power function to curve fit for those data points. Now, there's a trick. click on display equation on chart right here. If so, Microsoft Excel squeeze out the equation which is used to curve fit showing on the display right here. Okay, so this is the equation you used to curve fit those 4 data points. Okay? So I'm going to probably retype a little bit. So this y is a variable called CP, right? So this means CP. X is a Reynolds number. So I'm going to retype a little bit. Okay. So now I did a curve fit. So this is literally functional relationship using mathematical formula. Actually, it is Reynolds number to pressure coefficient. So you can use this equation to determine CP based on given Reynolds number. Okay? This equation is coming from those 4 data points. It's called curve-fitted empirical equation. Or sometimes called its correlation between Reynolds number and pressure coefficient. This is the real meaning of why you conduct experiments and then you plot the results. The purpose here is, let's go back to this whiteboard. The purpose here, you want to find out exactly what kind of relationship do you have between Reynolds number and pressure coefficient. Okay? We found it. Let me just write it down here. We found it. Based on plot and curve fit. We found CP is equal to 6820.7 times Reynolds number to the power of minus 1.009. Okay, we found that. In other words, this is the relationship between CP and Reynolds number. CP and Reynolds number. We found it. Okay? So let's go back once again to the plot. Okay. So this really answers lots of questions you may have. Suppose if your test condition Reynolds number is 700, you can either use this plot to sort of pick up the value, or use this equation, plug in Reynolds number 700 in your calculator, it determines CP corresponding to it, right? If your test section Reynolds number is 1200, either you pick up the data like this or plug in Reynolds number 1200, determine CP out of it. So this is very useful data. In other words, you're using this experiment, determine this relationship. Then suppose if you build a real pipe system, okay? The real pipe system, then happen to be in your real pipe system, your Reynolds number happened to be, I don't know, 1200. Then your question is, okay, how much pressure drop do we have? Well, you can determine that. 1200 comes with pressure coefficient of like 5. If the pressure coefficient is 5, you can determine how much delta P do you have. This is very, very useful information. Plots and together with squeezed out mathematical function that actually relates Reynolds number and CP. So this is why you have to conduct experiment, come up with plot, and then plot gives you equation. Okay? So part C, let's conclude this example problem. Part C says, is there any limitation for this equation or plot? Either way is fine. Limitations. Limitation of plot and equation curve fit equation. Limitations, of course. This is valid only in the range. In the range of Reynolds numbers 300 to 2000. So this equation can be applied only in this range. Outside of this range, you can't use this equation. Suppose if somebody asks you what is the CP at the Reynolds number 20, or what is the CP at the Reynolds number 5000, your answer is we don't know. We probably need to conduct another experiment to determine such a thing. In other words, if somebody says, what is the CP at right here? There's no data. It's outside of the data range which we determined this equation. So if somebody said Reynolds number 20, you probably want to conduct another experiment which covers maybe, I don't know, another 2 or 3 data points in low Reynolds number range to come up with this kind of data. Then you can tell. Now if somebody says, what if the Reynolds number is 2,500, you have no clue. You can extrapolate it to guesstimate, once again. But how do we know it's true? You need to probably conduct another experiment around here, around there, extend the data set range to tell that kind of answers, okay? So limitations obviously limited based on how much range of the data set you have. All right? So this is the very, very basic of why you do conduct experiment, why do you have to plot, and what does plot tell you. This is the ultimate purpose of why you're doing experiments. So let's do not forget about the very fundamental reason why you do. Okay? Let's stop here.